Hello guys, this is the 2018 edition of the Acids and Bases review. I already had a video up from last year, but I feel like there's some things I want to change up and go over again and do differently than what I did last year. And we're still going to go over some of the same topics here, but there's some things, especially about pH, that I want to explain differently, as well as titration, Bronsted Lowry theory, etc. And we're going to start with electrolytes. So electrolytes are substances with this ability to conduct electricity because they're able to break down into mobile ions. So when you dissolve them in water, they break down into their ions, and good examples of these are acids, bases, and salts. Okay, because acids, bases, and salts, when they are dissolved in water, they break up into their ions. And that's the key thing. They must dissolve into ions to be an electrolyte. So if something can't dissolve into ions, then it's not an electrolyte. So let's not get ourselves confused that it's both acids and bases as well as salts that can act as an electrolyte. Okay, and when I say dissolve into ions, let's talk about NaCl as an example. NaCl is a salt. And NaCl can break up into Na plus and Cl minus. Another classic example of an acid would be HCl. So it could break up into H plus and Cl minus. So the key thing about ions is that it's not just specifically a positive or negative charge, it's both. You can have either positive or negative ions floating around. So they can be positive ions or negative ions. So see here, Na plus, Cl minus, positives and negatives. Electricity could run through any substance here where you have mobile ions, mobile charges, not specifically electrons. Okay. And so there are different theories, two of them in particular that we're going to talk about, in which you can define substances as acids or bases if they follow this criteria. And the first one we're going to talk about is the main one, the Irenaeus theory. And based on the Irenaeus theory of acids and bases, acids have to be substances that can break up into an H plus ion. They have to give this up. Whereas bases have to have an OH minus ion. So that when you dissolve these substances in water, they're going to contain either an H plus ion to be an acid or an OH minus ion to be a base. Some of these examples to see include NaOH, sodium hydroxide, potassium hydroxide. These are classic examples of a strong base because they give up those OH minus ions. Whereas acids, on the other hand, classic examples, as I mentioned before, is HCl, is a classic one, H2SO4 sulfuric acid. All right, because they have those H's that they can give up. And so some of the special words that we should remember is especially hydroxide. So when you see the word hydroxide, you're going to think OH minus. So that's a word to remember, hydroxide ions. So it has both hydro for hydrogen and oxide for oxygen. Whereas H plus ions, you just call them H plus ions. The alternate theory, or technically called the Bronsted-Lowry theory, is another take on the acids and bases theory. So it's not just about H plus and OH minus. There are other substances that can fall under either category, but they follow a different way. And so this is all about the protons, okay? Protons are essentially which is essentially the same as H plus. So I'm going to do this in purple. So acids are the proton donor, so they give it up, whereas bases are the proton acceptor. So what does that mean? So let's look at an example reaction here. Let's have HCl be dissolved in water. And so it's going to break up into its Cl minus ion and H3O plus. So what is H3O plus? This is another word you have to remember. So this right here is called the hydronium ion, which is essentially H3O plus. Hydronium, when they say hydronium, is H3O plus. This is also another indicator of an acid. Also used to hint acids, to describe acids. Okay, the presence of H3O plus is another way to describe an acid. Okay, so we just have HCl placed in water. And when it comes to the Bronsted-Lowry theory, you're going to have substances that act as acids and those that act as bases, whether or not they give up the H plus or they accept the H plus. In this example, we have HCl being dissolved in water. So HCl going forward donates that H. See here? It goes from HCl to Cl minus. That H disappears, so this makes this an acid. So let's put this acid. Now, what about water on the other hand? H2O becomes H3O plus. What did it do? It accepted the proton to become H3O plus. So that makes water in this example the base. All right. So water, although it's a neutral substance, can act as either an acid or a base. It has this dual nature here. Okay. So on our left side, we have an acid-base pair. And on the other side, we're again going to have an acid and a base. And this is where we come into play with conjugate acid-base pair. It only falls under the Bronsted-Lowry theory. All right. So on this other side, we're going to look at Cl minus, going in the reverse direction. This is how you identify the acid bases on the other side. Going in the reverse direction, we have Cl minus becoming HCl. How did it become that? It accepted the proton, and on this side, H3O plus donated the proton to become H2O. So now here we have Cl minus becoming the base, and then H3O plus becoming the acid. All right. And then now we could identify acid-base conjugate pairs. So in this case, we're looking at a pair of substances that act as an acid on one side and as a base on the other side. So HCl will be paired with Cl minus. That's an acid-base conjugate pair. And then H2O on this side will be the base, with the H3O plus being its acid conjugate pair partner. Okay. So that's what we mean by acid-base conjugate pairs. You take a substance and figure out its opposite partner on the other side. What does it become on the other side? So I'm going to do another example where this time we have NH3 plus H2O. Okay, I just add that for technicality. And so this is going to become NH4 plus and OH minus. Looky there, we have the hydroxide ion there again. So now we're thinking about, oh, hydroxide ion. Maybe we're thinking about this might involve a base. So this is a way to prove that some other substances without the OH minus ion can be bases. All right, and so we're going to apply the same analysis here, and we're going to see that NH3 accepts a proton to become NH4 plus. So that makes NH3 a base, which is why you can have substances without OH minus, without OH in there, to be bases because they can accept protons. Ammonia, NH3 is a common one. And so on the other side, its corresponding partner, its conjugate acid, will be NH4 plus, ammonium. Okay, so that makes, in this case, water being the proton donor on the left side, an acid. So this is the dual nature of water. Depending on who it's reacting with, can act as either an acid or a base. And that means on the other side, its base conjugate partner will be OH minus. Look at there, OH minus always indicates base. And so let's finish this example off by identifying acid-base conjugate pairs. NH3 is the base paired up with its acid partner, NH4 plus. And then in this case, H2O acts as the acid paired up with its OH minus base partner. Okay, and that's it for Bronsted Lowry theory. It's kind of tricky, especially with acid-base conjugate pairs, but if you carefully analyze it, then it won't be as bad. Then we go on to this thing called pH. It's a logarithmic unit, and it runs on a scale of 0 to 14, and it helps to describe whether something's an acid or a base or even neutral. And here it measures the H plus, H3O plus concentration, so hydrogen ion and hydronium ion concentration. Okay, so acids are described as those with pH levels below 7. All right, so as long as it's below 7, it's an acid. Neutral ones are equal to 7. An example of that would be water, for the most part. Water is mostly neutral. Bases are above 7. Sometimes you could have those that go decimal-wise or even above 14, but those are very rare cases, and we're going to stick to the simpler side of going on a scale from 0 to 14. Neutral is 7, below 7 is acid, and above 7 is a base. Now, this is a tricky thing about pH. Because pH is a logarithmic unit, you get the pH from measuring the concentration of hydrogen and hydronium ions. So concentration, remember, we measure it typically with molar. So if you have something, an H plus concentration equal to 10 to the negative 1 molar, then you have to use log in order to figure out the pH. But we're going to skip over that complicated process of using log and just use a shortcut. What it essentially is that we're looking at the exponent of 10 here. So what this indicates is that relative to other things, for example, we're going to look at other concentrations of 10 to the negative 4, 10 to the negative 8, and then 10 to the negative 12 as an example. 10 to the negative 1 compared to the ones below it is really strong. Okay? And so what this equates to as a pH level, we're going to look at its exponent of 10 and just take away the negative sign and just use the number. So this equates to a pH of 1. Following that, this pH is equal to 4, pH equal to 8, pH equal to 12, okay? And so we can see that with a higher concentration, 10 to the negative 1, you have higher concentration of H+, you're more acidic than those below it. 10 to the negative 12 means you have so little. Remember that negative exponents mean really, really, really long decimals with zeros between the decimal point and the number, okay? So 10 to the negative 12 means a lot of zeros after the decimal. All right, so that's a small concentration, which means it's going to be very weak acid. It's probably going to be more basic, which is why it comes out to a pH of 12, which means it's a base. Okay, so as additional practice, let's identify these. This one's an acid, this one's acid as well, this one's a base, and this one's a base. Now, because pH is a logarithmic unit, which goes by factors of 10, we change our pH units based on the factors of 10. So what do I mean by that? So let's say, for example, we have a pH starting at 1, and then we suddenly change to a pH of 3, okay? Every pH unit equates to a factor of 10. So let me write that on the side. Every pH unit equals a factor of 10. Okay, so in our example here, we have a pH change of 2 units. So I'm going to edit this in green. So we have a 2-unit difference, which means we're changing up by 10 to the second. So it's a 100-fold change, okay? Remember that we're not going to change that 1. We're going to change the number of zeros after that. So factors of 10. So 1 pH unit equals 10. Molarity difference. pH unit of 2 unit difference means 100. 3 units means 1,000. 4 units means 10,000. All right? Now think about this example. Here, we are becoming from a pH of 1 to 3. So becoming more basic. So, which is also less acidic. So the H plus ion goes down by a factor of 10. So that's how you analyze a pH change like that. And I'll make another box to the side so that we can see that pH unit here, and then factor of 10. Okay, so 1 pH unit, 2, 3, 4, 5, 6. So that we're able to see how it changes. So this is 10, 100, 1,000, 10,000, 100,000, and then 1 million. Shortcut, count out the number of zeros. Make sure it matches. So if you change by 1 pH unit, you increase or decrease by 10. 2 units, up or down by 100. 3 units, up or down by 1,000, so on and so forth. All right, now on this slide, I've come up with some example problems for you guys to practice because I find this topic to be particularly tricky. So you should pause this because in the next 5 seconds, I'm going to post up the answers in a quick instant. So pause it and then wait, and then the answers will pop up. And then now I'm going to stop talking and put up the answers. And here are the answers. Check if you're right. If not, go back in the previous slide to go over the skills and things you need to go over again. Okay? Now moving on. Finally to indicators. This can be tricky, but honestly, it's a reference table use. It's all you need to know is how to read this reference table. So here we have our indicators. The most common ones we use in reality are phenolphthalein, which I showed you guys in class, and litmus paper. You might have seen litmus paper in the past before. But anyway, here we have indicators and the approximate range for color change. All right, so the color will change somewhere between these pH levels. So it not necessarily mean it starts to change at 3.1 and finish changing at 4.4. That's not what it means. It's not a gradual change from red to yellow within this range. All it is that, let's say an example of 3.5, it can instantly change from red to yellow. It's not gradual, no mixing of colors. So, but it can also change at 3.1, and it could also change at 4.4. But the easiest way to remember is that if you are above the range, then it's the second color. Okay, so if we're looking at methyl orange, if we're above 4.4, we're yellow. If we're below the range, then for sure we are red, this first color. Sometimes the change can happen in the middle. It's not always going to be like that. Very rarely there'll be questions like that. They'll be more strictly above or below. So that's the easiest way to interpret this table. Okay? Then we go on to this thing called neutralization. And it's essentially a reaction between an acid and a base. Something that's strictly an acid and something that's strictly a base. And they come together to make water and a salt. So let's write this out. Acid plus base make water and a salt. So key thing is that another phrase you could remember for neutralization is ABS, which stand for acid, base, salt. Because the one thing that a lot of people tend to forget is the salt part. Water can easily be seen as something that's being made there, but the salt part is the one thing that kids forget often. So abs is a good way to remember that. And if we look at an example reaction, let's look at HCl and sodium hydroxide. Okay? So they're going to make water and a salt. But how do we identify the salt? So let's see here. How is water even made? We take the H here and the OH here, and you make the H2O. So I'm going to color code this. That means the remainder partners that are left behind become the salt. Na and Cl. Together, they make NaCl. So quite often, when you have neutralization questions, the tricky thing is identifying the salt. So you just take the remaining partners and they make the salt. And so titration is a laboratory process that is often used for neutralization reactions, to react acids and bases together. So what the setup looks like here, you have a ring stand, and here you have a little beaker of either an acid or a base, and here you have this burette filled with the other one, and they have this stopcock here, that you can turn to allow base or acid to go through little by little. And then you also mix in an indicator, all right? So what I showed you guys in class was an acid at the bottom titrated with base from the burette, and I added 2 drops of phenolphthalein indicator to sort of indicate the endpoint or neutralization part, which is the end of the reaction, okay? So that we know that we have reached our endpoint. So this indicator has the color change, and when the color changes, then we know we've reached the end. All right. And so questions related to titration will be calculation based. And so when we say endpoint, we mean the moles of H plus equals moles of OH minus. Going back to solutions, we learned about molarity equaling moles of solute over the liters of solution. Okay, so getting the moles of the acid to equal the moles of the base, we essentially get this equation to be mass of the acid times the volume of the acid equaling this. Moles of the base, molarity of the base equaling the volume of the base. So that is our equation right here that we need to use. And the tricky thing is to identify the values that are given. So you need to read those questions carefully. The cool thing is that you don't have to convert this to liters. You can use mLs, and it'll be consistent like that. So the tricky thing again is to identify your acids and base and making sure you read the problem carefully to pick out the values you need to solve the question. Okay. And so that leads us into this final slide. What if I can't tell if it's an acid or a base? Because you're looking at all these substances and you're like wondering, it's like, how the heck do I know if it's an acid or a base? Well, use the reference table. That's all I could tell you. If you can't get through half of this test without using the reference table. It's not that bad, okay? So there's table K and there's table L. Table K gives you the acids. And if you look here, all of them have the H in front, all right? Except these two are organic acids, carbonic acid and ethanoic acid. If you see carbon there, it's an indicator that's an acid. Not necessarily a strong one, it's more of a weaker one. Then you have table L for the bases. Common ones definitely have the OH in the end of it. OH, OH, and OH. Ammonia, as I said before, going with Bronsted Lowry theory, it acts as a base because it's a proton acceptor. No electrons, just protons. So that's why it acts as a base. It's on the weaker side as well. Now, you'll see here that bases have the OH at the end. And then you look at this one, ethanoic acid on the table K side. Why does it have an OH here and it's an acid? Well, look here again, it has carbon. Organic substances are typically on the weaker acid side, all right? Even its name is ethanoic acid. And if you rearrange the letters, you get that H out in front because based on its structure and all that. All right, now that's the end of this video. Hope this was helpful. You better study your butt off going through this video, going through examples, identifying things you don't understand. Ask me questions, guys. Hopefully you'll come to review Tuesday before the test, either during lunch or study hall. All right, take care, guys.